This is buffer recipe number 3, labeled number 3 in your notes. And you'll notice we've taken a weak acid and we've combined it with a strong base. And this is not a titration, but is simply adding a strong base to neutralize some of the weak acid. But what we have right now is not a conjugate pair. We have a neutralization reaction. So the first thing to do to find out if we do in fact have a conjugate pair when the dust settles here is to do an IRF table for the neutralization of acetic acid with KOH. That's a one-way irreversible reaction to give us potassium acetate and water. So let's see what we have once this reaction goes forward until the limiting reactant is all used up. In our IRF table, we need initial amounts of acetic acid and KOH. We're given volumes and molarities, so we can figure out the moles of acetic acid by multiplying the volume given by the molarity, 0.8. That gives us 0.096 moles. And then we can also figure out the moles of KOH in the same way. So we're given a volume and a molarity, and we'll multiply those to get 0.042 moles. So that's what we start with. That's what's initially put into the beaker. We know these two reactants will neutralize one another. The question is what's left at the end of the reaction. So we put the initial moles in to our IRF table, and we can see, because these react in a 1-to-1 ratio, we can see pretty clearly that the KOH is limiting and there will be acetic acid left over or in excess at the end of the reaction. However, there will be no KOH left, called the limiting reactant. We can't forget though about the product. The product is the potassium acetate. And so now also in the beaker we have 0.042 moles of potassium acetate. There we have our conjugate pair, and therefore we have a buffer. We'll set up now the equilibrium that defines the buffer. We can write this as acetic acid and the acetate, the equilibrium between those two. Remember, they have to straddle the equilibrium if they're a conjugate pair. So we have acetate and H3O plus on the product side. The IREC table for this, we take those amounts in the final line of our IRF table and we put them into the initial line of the IREC table. And then away we go. If we put that we have 0 moles of H3O plus initially, we know we need a shift to the product, so we get X moles of each product, we lose X moles of reactant, and now we have equilibrium amounts of our reactants and our products. To get the concentrations, we will divide by the total volume without worrying what the total volume is. This is now an acid dissociation, so it's going to be a Ka expression that's going to help us solve for X. So we'll write the Ka for acetic acid. That would be the acetate concentration times the H3O plus concentration, all divided by the H3O plus, not OH minus, divided by the acetic acid concentration. So because it's pH we're after, we'll look for the molarity of H3O plus. We'll solve for that. So we'll rearrange the equation so that we're solving for H3O plus. Which will be given by the Ka multiplied by the ratio of acid over conjugate base. Leave the Ka there for the moment. Put the numbers in for the molarity. Those come from the equilibrium concentrations we have in our IREC table. And once again, we'll get rid of those values of X in there if X is small enough to do that. So we just have 0.054 divided by 0.042. This again is when X is much smaller than 0.042. And the number we get here is then the molarity of the H3O plus. Take minus the log of that to get to our pH. Happens to be an acidic buffer, this time created with a weak acid and a strong base.